All right, the topic that we're going to be talking about here is going to be differential equations and separation of variables. Separation of variables is going to be a special method to solve some of your differential equations. This method is only possible if we can write the differential equation in this form. b of y dy equals a of x dx, which means you're going to have some function in terms of y dy and then some function in terms of x times dx. We call this separation of variables because we need to move all of the x's, including the dx, to one side of your equation, typically the right, and all of the y's, including the dy, moves to the other side of your equation. Now, a differential equation is just going to be an equation of a derivative, which means you're going to have dy dx equals or whatever in this. So we're going to find the general solution of dy dx. Once again, this is a differential equation because this is the equation of a derivative. And the particular solution, whose initial condition is y of 0 equals 1. This is a point that is on our original function y. We do not know what y, the y function is yet, and we're going to be using separation of variables in order to determine what that equation is in terms of y. That solution or that equation in terms of y will be called our particular solution. All right, so we're going to separate the variables here, and so we'll do so by moving the y's to the left, x's to the right. So e to the negative y, this term right here has a y on it, so we're going to move this over to the left side by dividing it because there's multiplication in between here. The x's here, we're going to keep these on the right side, and we're going to move dx over to this side by multiplying it. That is going to give us 1 over e to the negative y dy equals 3x squared dx. So one of the mantras you want to try to remember here is you are going to separate and then integrate. All right, so we are going to be integrating the left side of our equation and the right side of our equation because just like with regular equations, it stays a balanced equation as long as whatever you do to the left side, you do to the same thing to the right side as well. Now, before taking the integral of the left side, I'm going to change 1 over e to the negative y to e to the y. That'll just make things easier because the negative exponent tells us to move that to the numerator. Now we can integrate, which is going to give us e to the y dy equals x cubed, and then we're going to put a plus c on this because these are indefinite integrals. Now, you're asking, why didn't we put a c on the left side also? Well, think of it this way. You would be putting a c, or a constant, over here. We don't know what that constant is. You would put a constant over here as well. What we are going to be doing is solving for y, which means moving everything over to the right side of our equation. Well, when I move this constant over to this side of my equation, a constant minus or plus a constant is still going to be a constant. Remember, we don't know what that constant is. So if you put a plus c here and a plus c here, and then you move this constant over here, you're still going to be left with a constant. So as a result, really what we do is just put plus c on one side of the equation. Okay? All right, so our next step is to isolate, the next step is going to be determining what our C value is. All right, so we can determine what the C value is by plugging in our initial condition. The initial condition was y of 0 is equal to 1, which means e raised to the first power dy is equal to 0 cubed plus c. I'm sorry, the dy is not going to be on this. Let me take that. When you integrate, the dy goes away. All right, so then what that leaves us with then is going to be c is equal to e to the first power, or e. You can now take this and substitute it back in to our equation, giving us e raised to the y is equal to x cubed plus e. Our next step is to solve for y, or isolate the y. So anytime that you have e raised to a power where your variable is in your power, the way that we get our exponent, our variable out of the exponent, is by taking the natural log of both sides of our equation. All right, so that will give us natural log of e raised to the y equals the natural log of x cubed plus e. Now, your properties of logarithms say that if you have the natural log of something to a power, you can bring that exponent to the front of your logarithm. All right, so what that will give us then is y times the natural log of e is equal to the natural log of x cubed plus e, and the natural log of e is 1, giving us y is equal to the natural log of x cubed plus e. And that is our particular solution to this differential equation and this initial condition. All right, so let's take a look at the next one. We'll work through this one together, and then we'll do some individually. So once again, we're going to move the y's to one side. So we're going to multiply the y squared over to the left side, giving you y squared dy. Multiply dx over to the other side, giving you x dx. Your next step is to integrate both sides of our equation. So we get y cubed over 3 is equal to x squared over 2, and then we tack on our constant. Now, once again, this is our initial condition over here. Y of 0 is equal to 1, so we substitute 1 in for the y value, and then we substitute 0 in for the x value. And we solve, finding that c is equal to 1/3. All right, so we're going to take this and plug it back in, giving us y cubed is over 3 is equal to x squared over 2 plus our constant of 1/3. All right, so our next step after we plug in c, we are going to solve for y. So just reiterating our steps here. We separate the integrals, and then we integrate. Find out what c is by plugging in your initial condition, and then you're going to solve for y. All right, so we're going to multiply by 3. That's going to give us y cubed is equal to 3x squared over 2, and then 1/3 times 3 is 1. And our last step here is going to be taking the cube root of all of this. So we get cube root of 3x squared over 2 plus 1. That is our particular solution. All right, so the next one says find the general solution of this equation. So we need to separate our variables. Now, we need to apply a property here to help us separate, because we may think of this as one term with x's and y's in it, which is partially true. But we can still separate by rewriting this as dy dx is equal to e raised to the 2x times e raised to the y, because your algebra here says that when you multiply two things together that have the same base, then you add your exponents. For example, x squared times x cubed would be x to the 5th power. You're adding the exponents. That's what we have right here. So what we're doing, it really is undoing this right here into this. So now we can separate. We bring this term over to the left side by dividing it, move this term over to the right by multiplying, giving us 1 over e to the y dy equals e to the 2x dx. All right, so now we need to integrate. But before we integrate, I'm going to rewrite this as e to the negative y dy e to the 2x dx. All right, so this is going to involve u substitution. U substitution where this is our exponent right here. That's going to be u. The derivative of this is negative dy, which means we need to put a negative right here. So putting a negative here means I also need to put a negative out in front of my integral. All right, over here, this involves u substitution as well. The derivative of this is 2 dx, which means I need to put a 2 here and a 1/2 out in front. So we'll go ahead and do that, 2 and 1/2. Now when you integrate, this would be the integral of e to the u du, and I'll just go ahead and write it out so that you can see it the first time. I normally don't write all of the steps here. And so this becomes negative e to the u, which the u value for this particular part is negative y. This will be 1/2 e to the u, and the u value for this integral is 2x. And then we've got our plus c. All right, so now we're going to find our c value by plugging in our initial condition. The initial condition is y of 0 equals 0. So that will be e to the 0 power, negative e to the 0 power, and 1/2 e to the 0 power, which means negative 1 equals 1/2 plus c. Therefore, c is negative 3/2. All right, we're going to take this and plug it back in right here, giving us the equation negative e to the negative y equals 1/2 e to the 2x minus 3/2. All right, so now we proceed to solve for y, or isolate the y. All right, so the next step is going to be moving the negative over to the other side by dividing it. That will give us e to the negative y, and it makes these the opposite sign, so I'm just going to switch the order and call this positive 3/2 minus 1/2 e to the 2x. All right, so now we're going to take the natural log of both sides of our equation. taking the natural log of the left side will leave us with negative y equals the natural log of 3/2 minus 1/2 e to the 2x. And the last step is dividing by the negative, giving us negative natural log 3/2 minus 1/2 e raised to the 2x power. That is our particular solution to this differential equation and initial condition. All right, so the next one, we have this differential equation up here. This time it's not dy dx equals, but we still have dy dx in our problem, which makes it a differential equation. And so what we're going to do then is isolate dy dx first, and then we're going to move our variables on one side or the other. All right, so the first thing I would do is move the xy over to the other side. So you have 1 plus x squared dy dx is equal to negative xy. Then I'm going to divide by the parenthesis, giving me dy dx is equal to negative x y over 1 plus x squared. Now I'll move the y's to the left, x's to the right. So I'll move this y right here to the left side by dividing it, giving us 1 over y dy equals negative x over 1 plus x squared dx. All right, so now we're going to integrate. The integral of 1 over y dy, that's pretty basic. That's going to be natural log, but make sure that you put the y in absolute value bars. Now the integral of this is going to involve u substitution, so I'm going to take a little bit of time here and work through this. I'm going to make this 1 over 1 plus x squared times, and I'm going to bring the negative out front and put the x next to our dx. Now if we let the u value be our denominator right here, then du would be 2x dx. So that means I need to put a 2 here and a 1/2 out in front. All right, so let me go ahead and do that, and I'll make this a negative 1/2 in front and a 2 right here. So now what that gives us then is negative 1/2 integral 1 over u du, which is negative 1/2 natural log of u, where u is 1 plus x squared, and then we have a plus c on the end. Now the absolute value bars on this one are not absolutely necessary. We usually kind of put those there out of habit. When you do an integral, you always put absolute value bars around this. However, 1 plus x squared is always going to be a positive number. Therefore, the absolute value bars, that's why they're not absolutely necessary, but putting them there does not hurt anything. All right, so now what we need to do is find out what is c, and that's giving our initial condition. So we're going to substitute in, giving us natural log of y, which is 2, equals negative 1/2 natural log of 1 plus 0 squared, which is 0, plus c. All right, well, that's going to give us natural log of 1 here, which is 0, times anything is still 0, which means c is equal to the natural log of 2. All right, so substituting that back in to here is going to give us the natural log of the absolute value of y equals negative 1/2 natural log 1 plus x squared plus natural log of 2. All right, so the next step, this problem is a little bit different than the others in that we have natural log of y. How do we get rid of natural log? Well, we do the inverse, which is going to be e, and therefore we do what is called exponentiating both sides of our equation. And when we exponentiate both sides of our equation, it's going to look like this. You're going to have e raised to this power equals e raised to this power. Now, e raised to the natural log of something is going to be that something. That's properties from logarithms back in pre-cal and algebra 2. So what we end up with then is going to be the absolute value of y equals e raised to the negative 1/2 natural log 1 plus x squared plus natural log of 2. Now, how do we get rid of the absolute value bars? Well, whenever you have an absolute value, that means that can equal either a positive or a negative value. For example, if you took the absolute value of x is equal to 9, that means x could either equal a positive 9 or a negative 9. So what we get then is we can ditch the absolute value by saying this is equal to plus or minus e raised to this power. Now I'm going to show you a little simplifying tool here from pre-cal. And it's just like what we did before, where you have e raised to something plus something else. We can write this as e raised to this power times e raised to this power, because when you multiply with the same base, you would be adding your exponents. That would give you this right here. And we do that because e raised to the natural log of 2 simplifies down to 2. That means your answer here would be y equals plus or minus 2e raised to this power. Now, just something for the AP exam. This step right here, going from this simplifying to this simplifying, is not necessary on the AP exam. You might have a multiple choice question where this is your simplified answer. However, on a free response question, it is not necessary to simplify this into this. All right, so what I want you to do is pause the video, take a look at this differential equation, and I want you to find the particular solution with this initial condition. Once you think you have the answer, unpause the video, and then you can reveal the solution here. So once again, go ahead and pause this video. All right, so one thing that we haven't come across yet is this situation down here when you end up with a plus or minus. And on the plus or minus, we need to figure out which one is it going to be. Is it going to be -3 plus this, or is it going to be -3 minus this? and that we determine by our initial condition right here. And so that means if I plug 1 in for x, I have to get 1 for a y value. All right, so if we plug 1 in for x, that's going to give us 6 minus 6, which is 0. E to the 0 power is 1, and 2 times 1 is 2. Therefore, in order to get 1 as an answer, let me backtrack. This should not be a negative 3, that should be a positive 3 because I divided by my negative right here to get this. All right, so remember this came out to a 2, and so in order to get 1 for a y value, that means we have to use the minus. So it would be 3 minus 2e raised to this power. And that will be our final solution. You must make that final step in determining which one is it going to be. Is it going to be plus or is it going to be minus? You always use your initial condition to determine which one it is. All right, so what I want you to do is read through this free response question. This was a free response question from a few years ago, and I want you to see if you can come up with the solution here. I'm giving you all parts of the free response question, so some of it might be differential equation solving, some of it may not be. You have to interpret what the question is asking. So go ahead and pause the video, try to reason through what your answer should be, and then you can unpause the video to see what the solution is. All right, so welcome back, and you can see here that dB dt is the rate at which the bird is gaining weight. So at 40, it is gaining weight at 12 grams per day. At 70, it's gaining weight at 6 grams per day. Therefore, the bird gains weight faster at b equals 40 because, and this is your notation for because, dB dt evaluated when b is 40 is greater than dB dt evaluated when b is 70. All right, so here's the same stem, different part. This is part B for the question, so go ahead and pause the video, read through this, and see if you can come up with a conclusion and the reasoning for that conclusion. All right, so what we had to do is we had to take the second derivative of this. So what I did first was distribute to give us 20 minus 1/5 b. Taking the derivative of the 20 is 0, and the derivative of this gives us negative 1/5 dB dt. Remember, this is with respect to time, so we have to put dB dt here, which dB dt was this from up here. And so substituting in gives us this equation here. We set it equal to 0 because we need to do a sign chart with this. And the sign chart says from birth at when b is 20, between there and 100, your second derivative comes out negative, and your second derivative comes out positive afterwards. Or second derivative negative means that a graph of your second derivative should be concave, or your graph of your function should be concave down between 20 and 100. But you can see here that our graph is concave up in this situation. So therefore, this cannot be the graph of this function. All right, so the next problem here, go ahead and read through this. You'll notice this one does say use separation of variables to find y equals, and so you're going to go through the separation of variables process, which is what most of this lesson has been on. So go ahead and take a few minutes to work through this particular problem. Pause the video, and then when you think you have your solution, you can unpause it and see what the actual solution is. Okay, well, when you go through the process here, you have u substitution that you have to use because the denominator will be u, and the derivative of that is negative dB. So you got to put a negative here and negative here, giving us negative integral 1 over u, which is negative natural log, absolute value. Plugging in your initial condition, which was 0, 20, so plugging those values in, you end up with c as negative natural log of 80. Substitute this back into c, giving us our equation here. So the next thing I did was divide by the negative to get rid of that. Makes these change signs over here. And then I exponentiated both sides of my equation. So e raised to the natural log of this is equal to this. So that's what we have here. And then we have e to this side over here. So I dropped the absolute value bars, putting a plus or minus in front of the e. I also made this e to this power times e to this power, and e to this power is 80, so I put that in front of the e here. Now make sure you put it as a coefficient of the e, not in front of the plus or minus over here. There's a big difference there. All right, so then subtracting 100, then dividing by the negative, you end up with 100 plus or minus this. And we do have to use our initial condition to determine if it's plus or minus. Plugging in 0, you would need to subtract 80 in order to get 20 as our result. All right, so that concludes that. And this is the scoring for that particular year on the AP exam, so you can see the breakdown of points on how those were given.